Hello friends, I welcome you in lecture number 5 on residues. In this lecture we are going to discuss about one important result of complex analysis known as Cauchy's residue theorem. Using this result we can evaluate some complex integrals easily. So we will understand what is Cauchy's residue theorem and we will see how to apply Cauchy's residue theorem to evaluate complex integral. So first we understand what is Cauchy's residue theorem. So for that, suppose we consider some function. Let f of z be a complex function which is analytic at all points except finite number of points, say z1, z2 up to zn. Suppose f of z is analytic at all points except finite number of points which are z1, z2 up to zn, and these points are inside some simple closed contour C. That means z1, z2 up to zn are inside some simple closed contour C. So again I repeat, the function f of z is analytic at all points except finite number of points, say z1, z2, zn, which are inside the simple closed contour C. Now this z1, z2, f of z is analytic at this point, f of z is not analytic at these points only. So this z1, z2, zn are isolated singular points. They will have deleted neighborhoods in which they will be analytic. So this z1, z2, zn are isolated singular points of given function f of z which are inside simple closed contour C. So our interest is in those isolated singular points of f of z which are inside the simple closed contour C. The points which are outside and on the simple closed contour C are not of our interest for this result. So if this condition is satisfied and if we are interested in the integral of f of z along this simple closed contour C in counterclockwise direction, then this integral is nothing but 2 pi I times sum of residues of f of z at these points which are inside C. Sum of residues of f of z at z1, z2, zn. So if f of z is analytic at all points except finite number of points z1, z2 up to zn which are inside simple closed contour C, then integral of f of z along this contour C has value 2 pi I times sum of residues of f of z at these points z1, z2, zn. So here if this assumption is satisfied, then we only have to find out residues of f of z at those points which are inside the simple closed contour C. So this is Cauchy's residues theorem. So here we have written Cauchy's residue theorem. Let f of z be analytic inside and on a simple closed contour C except for a finite number of singular points z1, z2, zn. Here we are interested in the interior portion of contour C. So f of z is required to be analytic inside and on the simple closed contour C. We don't have to worry about analyticity of f of z outside the simple closed contour C. So suppose f of z is analytic inside and on a simple closed contour C except for a finite number of singular points z1, z2, zn which are inside C. then the integral of f of z taken counterclockwise around this contour C equals 2 pi I times the sum of the residues of f of z at z1, z2, zn, that we can represent mathematically in this way also. Integral is given by 2 pi I times sigma residue of f of z at z equal to zk, where k is running from 1 to n. So we understand with the help of example. Here we are asked to find out this complex integral using Cauchy's residue theorem, and this contour C is the circle mod z equal to 3, that is circle with center 0 and radius 3, and function is z plus 1 over z square minus 2z. So first we write down what is given function. Let f of z is z plus 1 over z square minus 2z, and this is rational function, so it is not analytic at those points at which denominator is 0. So here z square minus 2z, this we can rewrite as z times z minus 2. So denominator becomes 0 at z equal to 0 and z equal to 2. So clearly f of z is analytic at all points except z equal to 0 and z equal to 2. And if we consider this circle mod z equal to 3, suppose this is this circle mod z equal to 3. This is just for understanding, so this is rough sketch. Suppose this distance is 2, so this is this circle mod z equal to 3 and z equal to 0 and z equal to 2 are inside the given simple closed contour mod z equal to 3. So f of z is analytic or at all points except z equal to 0 and 2, which are inside contour C, which is mod z equal to 3. So here requirement of Cauchy's residue theorem is satisfied. F of z is analytic at all points inside and on the simple closed contour C except these 2 points. Okay, so finite number of points where function is not analytic are allowed inside the contour. So here, so we can write more precisely that f of z is analytic at all points inside and on C except z equal to 0 to which are inside C. So therefore we can apply Cauchy's residue theorem. So to apply Cauchy's residue theorem, we require residues of f of z at z equal to 0 and at z equal to 2. So first we find out residues of f of z at z equal to 0 and z equal to 2. Now f of z is nothing but z plus 1 over z into z minus 2. So to determine the residue at z equal to 0, we rewrite our function as z plus 1 over z minus 2 divided by z, and suppose this is denoted by phi of z. So where phi of z is z plus 1 over z minus 2 and this is analytic at z equal to 0. It is rational function. Its denominator becomes 0 at z equal to 2. So it is analytic at z equal to 0, and value of phi at z equal to 0 is 0 plus 1 divided by 0 minus 2, that is minus 1 by 2, which is non-zero. So if we recall the result, that f of z, if our function f of z can be written in this way, phi of z over z minus z0 raised to m, where phi of z is analytic at z0 and phi of z0 is not equal to 0, then f of z has a pole of order m at z equal to z0. So here z0 is 0 and phi of z is analytic at z equal to 0. Value of phi at z equal to 0 is non-zero, and here power of z minus 0 is 1. Therefore f of z has a simple pole or a pole of order 1 at z equal to 0, and if function has a pole of order 1 at z equal to 0, then residue at that point is nothing but value of function phi at z0. So using this result, we can easily evaluate residue of a complex function at a given point. So here our f of z is written in this form, phi of z over z minus 0, where phi of z is analytic at z equal to 0 and phi of 0 is non-zero. Therefore f of z has a simple pole at z equal to 0, and residue of f of z at z equal to 0 equal to value of function phi at z equal to 0, which we have calculated as minus 1/2. So this is the residue of f of z at z equal to 0, which we denote by b1. Similarly, we find out residue of f of z at another point, which is z equal to 2. So for this we rewrite our function as, instead of z in the denominator, now we require z minus 2 in the denominator. So we rewrite our function as z plus 1 over z, and in the denominator z minus 2. And here this is our phi of z, z minus 2, where phi of z is nothing but z plus 1 over z, and it is clearly analytic at z equal to 2, which is analytic at z equal to 2, and its value at z equal to 2 is nothing but 2 plus 1 divided by 2, that is 3 by 2, which is non-zero. So therefore f of z is written as f of z over phi of z over z minus 2, where phi of z is analytic at z equal to 2 and phi of 2 is non-zero. So therefore f of z has a simple pole or pole of order 1 at z equal to 2 also, and residue of f of z at z equal to 2 equal to value of function phi at z equal to 2, which is 3 by 2. This we denote by b2. So we have calculated residues of f of z at both the isolated singular points. So now we can write by residue theorem integral of f of z over c equal to 2 pi I times sum of residues of f of z at z equal to 0 and z equal to 2. So residue at z equal to 0 is b1 and residue at z equal to 2 is b2. b1 was minus 1 by 2, b2 is 3 by 2. So this is going to be 1, and therefore the value of integral is 2 pi I. So therefore integral of function z plus 1 over z square minus 2z along the simple closed contour C, which is mod z equal to 3, is nothing but 2 pi I by Cauchy's residue theorem. So in this way we can easily evaluate certain type of integrals using Cauchy's residue theorem. The only condition we require is our function f of z is analytic at all points inside and on the simple closed contour C except finite number of points z1, z2, zn. So this is all about today's lecture. In the next lecture we will do some more problems on Cauchy's residue theorem. I hope you like this lecture. Thank you very much.